Morning, everyone. Welcome. So let me share my screen. Maybe if I can. There we go. All right, so let's talk about the project a little bit first. So let's take some questions about the project. So you had a question? Yeah, go ahead. Yeah. Yeah. Right. So what you're going to do, and probably what you should start with, is you're going to read a memory address. And so there's a question in Slack from 13 minutes ago, and the person's not here, but I'm going to answer it. So maybe the person will watch the recording. I don't know. Load and store, there's no difference. It doesn't matter whether it's load and store or store. You're going to read an address. You're going to figure out if that you're going to read an address. You're going to turn it into a set number and a tag number. Obviously, if it's fully associative, there's one set, so you don't need a set number. So you get the tag out. You'll go and you'll look in the cache and you'll see if that tag is there. If it is, it's a hit. If it isn't, it's a miss. So load and store doesn't matter for this simulation. We're not simulating writing, and that would be more complicated, and we're not doing that. Okay, so load and store is no different. So you're going to take that address and you're going to split it into whatever fields you need to. So again, like I said, if it's fully associative, there's only one set, so there's no set field. Okay. If it's direct mapped, there are as many sets as there are lines, right? A set has one line in it, right? So you are going to take that address and you're going to split it into, so you take off, so however big your line is, that's going to be your offset field. You're just going to get rid of that, right? Because we're not doing anything with offsets in this either. We're just figuring out, is this block that I need, or this line? Again, a line and a block are the same thing. We're not looking at a particular byte, so the offset doesn't matter. So you're going to take your address, you're going to get rid of the offset, right? Just take it off, right? So if your line is, say your line is 4 bytes, your offset field that's 2 to the 2, right? So your line is 2 to the 2 bytes, right? So your offset field is going to be 2 bits because it's the log of the line size. So you're just going to take 2 bits off the address. If it's direct mapped and there are 2 to the 8th bytes in your cache, well, you have to figure out how many lines are in the cache. We can go through that if you want. You figure out how many lines are in the cache, you take the log of that, that's the size of your line field. Okay. Good. But there's lots of examples of that in the when we were doing cache in class, where you figure out how many bits are in each field, right? Tons of examples, and that's what you're going to do in the program. Okay, so I had some people ask, do I have to convert hex to binary? If you can find a way to have all your parameters only be divisible by 4, you could do that. That might be kind of hard. But, it really isn't that big of a deal to convert hex to binary. You just make a method, and it's going to be just a kind of an if statement with 16, I guess it would be an if with 15 else's, right? And you're just going to return. So you take in a character and you'll return a string of 4 ones or zeros, right? So it might take some creativity to not convert hex to binary. And it might be easier just to write that darned if else statement. Did you have a question? No. Okay. You do not have to print. Well, you can print if you want, or I shouldn't say this, but maybe I shouldn't say this out loud. I'm not going to run your simulation. That's why you're turning in. So you need to turn in a little movie, a little screen capture of it compiling and running, because although I think about 11 people maybe have turned it in, and all but one have been in C++. One person did Rust. You go. I'm not going to run it. I want you to turn in a screen capture of compiling and running it. So I really don't care how you get your output. If you run the thing in CLion and get it out of there somehow and don't print it out, that's fine with me. What you need as output is the hit rate. So however you get that, that's up to you. So hit rate is going to be the number of hits divided by the total number of accesses. The total number of accesses is going to be however many lines are in that trace file, right? That each one of those is an access. You're going to count up how many are hits. That's your hit rate.
Ms. Rush.
Yeah.
I just had a quick question. I was a bit confused about what we count as like hits in between like stores and loads.
Stores and loads don't, they're no different. So you don't have to take in whether it's a load or store from the trace file. You're just going to take each address, and if it is in the cache, it's a hit. If it's not in the cache, it's a miss. So it's, yeah, nothing.
Okay.
Is that good?
Yeah.
Good. Okay. Any other questions? Okay, so let's look at, so these are the parameters. And, I got a question on Slack, which is a parameter, the cache size or the number of sets? Either one, so one's going to define the other, right? So you define what the associativity is. You define the block line. If you have as a parameter the cache size, you're going to calculate the number of sets. If you specify the number of sets, that's going to define the cache size. So I had one person, for the set associative, you define the n way. That is a parameter. You're going to say, is it 4-way? Is it 2-way? Is it 16-way? Is it 8-way? And so you're going to do fully associative and direct mapped. You can also do a number of these, right? You could do 2, 4, and 8 and compare it. You could do just 4, or, okay. Anyway, I have had, so this one, I've had people turn it in where they said, I'm going to model, I don't know, whatever they modeled. I think it was 64 sets or something like that. So if you model 64 sets all the time, that's going to define what your cache size is. If you're, if you define that and you define that and you say there's 64 sets, that then you calculate your cache size, right? Yes, I've gotten your pleas, but this has been open for a really long time. So, you could have been working on this for a while now. So yes, you're welcome to turn it in on Sunday and there'll be a late penalty. I'm sorry. Maybe I could lower it, but I can't push it out because I need to grade these things. I have deadlines too that I need. And then there's 400 of you. So I need to get these things in so I can grade them. It's due Friday. Well, I don't know. When is it due? If it's due Sunday, it's due Sunday. But is it due Sunday? Well, then I'm definitely not moving it out. We're not moving this. Because I got to grade these things. Right. Okay. So definitely don't Jones me for any more time because I got to grade these things. Yes, you have to use that. You can't compare them, right? You can only compare two different cache designs using the same file, right? So if you want to just use the GCC file and do that and make that your whole comparison, yes, you can do that. Yeah, you have to use the same file to compare. Go ahead. Yeah. Yep. Yeah, that's a good one. And the swim one, either one is fine. The other ones are there for you to kind of debug, right? And someone asked, can you edit those little ones, to, kind of check things? And yeah, you can do that. You could add lines to the ones, excuse me. But like the real comparison, you should use the GCC or the swim. So any ideas on why, why don't we just randomly generate addresses? I mean, I thought when I was writing this, I'm like, could we just randomly generate addresses? Any ideas why that wouldn't be a good simulation, just randomly? Go ahead. Yeah. Okay, what was your idea? Yeah, they're not random. That was a good answer. When programs are accessing addresses, it's really not random. So it had, to get a realistic cache simulation, you have to have realistic address requests, right? Because there could be arrays or there are repeats. I mean, the reason we have caches is because addresses are repeatedly asked for, right? So that was why I was like, oh, we can't really do random. We have to actually do trace files. And luckily for everyone, I found a trace file online. And it seems to, from the results I've gotten so far from the people that have turned it in, there are, the hit rates get pretty big, right? If even for relatively small caches, I think if you did random, the hit rates would be a lot smaller, right? So let's look at these questions. Wouldn't some of them have the same tag? I'm not sure what that question is. Yes, they're going to have the same tag, and then they'll have a hit. This is usually the format from actual code making the simulation. Yeah, so yeah, the GCC is actually, I guess it's a trace file from running the C compiler, right? So I guess the C compiler is written in C. It's kind of meta or, recursive. But so the gcc.trace is an actual run of GCC, right? So it's actual code. So the simulation is reliable or really realistic. So how many cache designs? Well, you have to do, in terms of cache design, like I'm calling cache design the associativity. So you have to do at least one set associative. You have to do fully associative, direct mapped, and at least one set associative. You're also going to have to have something to say about it. I think you should change at least the cache size. So maybe you're going to do a couple different cache sizes, and then you have to do 2 replacement strategies. So the minimum, I think I told someone the minimum number of runs would be something like 15. So you have at least 3 cache designs and at least 2 replacement strategies. And you want to do a couple of different cache sizes, right? To see, how does it change with cache sizes? So let's say 3. So that would be 18 minimum. Yeah, so the replacement strategy, yes, you would want to do the same configuration and the different replacement strategies and see which one is better, right? So keeping everything else constant, change the replacement strategy, right? And see which one is better. If the hit rates are really small for the fully associative, what would be causing that would be incorrect code. You did something wrong. They should be highest for fully associative. So you're going to have to look at your logic and figure out, because I can tell you, I've gotten some people have turned it in, and the hit rates for the GCC for the fully associative should be higher than the direct mapped and the set associative. So what's causing that is logic. I'm not going to go, argue about what, so the instructions say that n sets of 1 block is direct mapped, but I thought the number of sets always equals the number. Yes. Where that's saying the same thing. Yes. So, right. We can argue about semantics, but the number of sets equals the number of blocks for direct mapped. What makes the hit rates different for each cache design? So what makes the hit rate different? So let's think about direct mapped versus fully associative. Why should direct mapped is going to have a lower hit rate than fully associative? So why is that? So with direct mapped, I'm going to get an address, and there's going to be one possible place that can be. There's one line you can put that in. With direct mapped, it can go in any line, right? So those are the 2 extremes. Where direct mapped, there's one place, fully associative, there's n places it can go. So that means if you should happen to get 2 memory requests that map to the same line, it's going to be a miss. The whole rest of the cache could be empty, but you just happen to get 2 requests for the same, that map to the same line, that would be a miss. With fully associative, you you could put it anywhere, right? So you're going to fill up the cache in fully associative, where in direct mapped, you might not, right? So that's what makes the hit rate different. If you happen to get two things that collide in direct mapped, it's going to be a mess. In fully associative, anything can go anywhere, so you can always find a place. That makes sense, but that's why. Maybe you'll see it when you run your simulation. That was kind of part of the reason for doing this, is to kind of learn by force these things from running these simulations. How come we ignore? How come? Because I said so. Because I decided we don't have to model it any differently. So I don't know how to answer that, because I was trying to make it easy for you. I was trying to make it simple. Yeah. So if we were doing, a more complicated simulation, so load would be the simpler thing in a cache. You're just reading. Store would also involve a write, right? So a load would just be an access, and a store would be a write. So we'd also have to do something about, do we write main memory in addition to writing the cache? I think that's called write back. It would just make it a little more confusing. A stores involve, what's called like a dirty cache, where maybe the cache is different from main memory, because you're not right. Because if you wrote main memory every time you did a store, then what would really be the point of a cache, right? But I decided we're not going to model that. We're not going to worry about that. I think our trace files don't have instruction accesses either, which we could be doing that as well. We could do a instruction and data cache, but we're not doing that. So yes, you choose the size. Yep, you choose all of these things. Okay. All right. Okay, so let's look at, I kind of talked about this, but what kind of results should you expect? Also, let me repeat, you have to turn in a number of files. You have to turn in your code. You have to turn in a movie with, a screen capture with it running. I just have to know that you actually wrote something that you can compile and run. Like, you have to turn in your result, your like a PDF or doc with your paper. One person has not turned in the movie and the code. So if that's you, if you turned yours in, make sure you have all the files. So you might want to fix that before Sunday. Okay, so we talked about this. As associativity goes up, the hit rate should go. What's the answer? Who's got a guess? So associativity would be 1. Oh, you have your hand up. What's the answer? It should go up. Right, so I'm going to say associativity, direct mapped has an associativity of 1. Then there's 2-way set associative, 4-way, 8-way. Somebody, I was reading like the discussion, the extra credit discussion, and there was some 3-way in there, and that seems just weird to me. It should be 1, 2, 4, 8. Anyway, as the associativity goes up, the hit rate should go up. So for everything else held constant, the size, the block size, the line size, the cache size, everything else held constant, as the associativity goes up, the hit rate should go up. Fully associative should be the highest. Okay. All right, fully associative should have the best, where best means highest. Direct map should have the worst. Okay, as the cache sites go up, the hit rate should go up. Yes. The bigger the cache, the better, right? I mean, that kind of makes sense, right? You know, the more you have in your cache, the more likely you're going to have a hit. So everything else constant, as the cache size goes up, the hit rate should go up. More room in the cache should translate to more data in the cache, which should translate to more hits. What I've seen from the ones that have turned it in so far is the advantage of more associativity kind of becomes a diminishing return, right? As you get a bigger cache, the difference between fully associative and 8-way or 4-way gets a lot smaller, right? So a really small cache, you're going to see a big difference between direct mapped and fully associative. A giant cache is going to, you know, the improvement is going to be less. As the block size go up, i.e. more, the block size goes up. This is actually wrong. So bigger block size would be less blocks in the cache. Hit rate should go up. There's fewer. Bigger blocks should translate to more hits. This is actually a smaller effect than having a bigger cache and more associativity, but a bigger block should produce more hits. But it's not as pronounced. So I would say if you're going to pick two things to plot, you should definitely look at holding everything else constant. How does the hit rate change as the associativity goes up? And then this one, holding everything else constant, how does the hit rate change as the cache size goes up? And then replacement strategy, least recently used or FIFO, which one has a higher hit rate. It depends on the nature of the accesses, but least recent, like at best, FIFO and LRU are the same. In practice, least recently used should be better, should have a better hit rate. And the first few assignments turned in have shown least recently used to be better than FIFO. So that's what you should expect. So why is that? I mean, that's just like the cache thing, right? When you think about it, a cache is what you want to keep the most, like that's the time part of a cache, right? So we talked about a cache saves, you know, spatial, you know, what a cache does, it says, oh, if you looked at this thing in memory, maybe you're going to look at something near it. The least recently used says, if you looked at this thing recently, you're going to want to look at it again, right? So least recently used takes advantage of that. And we have found from the ones that have been turned in so far that I looked at, the least recently used does give a little better hit rate. It's not this huge difference, but it is a little better. All right, so we talked about this one. Why use trace files and why not just generate addresses randomly? Because if addresses were random, we wouldn't have caches wouldn't do any good, right? If it really was random, why would caches give us any advantage at all, right? Okay, any more questions on that? Oh, go ahead. So the question was a .zip. You can, whichever one is you would rather do. I'll take a zip file. Yep, you can include a makefile. Yes, that was the question. Yes, you can include a makefile and you can put it in a zip file if you want. Any more questions? So it's due Sunday. See, all this time I thought it was due Friday. All right. You have till Sunday. I expect to not get many more until Sunday. Right? The drawback of this is how many of you there are, and I have to grade them, sadly. So I'll get the TAs, but I really want to look at them. So if we think about if I spent 1 minute, that's 400 minutes. I know. So think about that. And I have other things to do in my life. Anyway. All right. So now we're going to go, unless there's any more questions. Okay. Back to, and now for something completely different, parallel processing. Let's look at this again. So let's look again. What is parallel processing? It's doing two things at once. And so obviously, this isn't not parallel processing. So the Flynn's taxonomy looked at two ways of thinking about doing two things at once. I can either look at multiple instruction streams, so run two programs. Or multiple data. So, multiple data would be more than one piece of data at once. Right. So this multiple data single instruction is vector processing. That's saying I have to do the same thing to all this different kind of data. I can do it all at once, right? So the example I use a lot is graphics, right? So I'm doing the same program. If I'm running the same thing, right? It's the same program on different pieces of data where each pixel would represent a piece of data, right? But I'm doing the same thing. Or any time of vector processing, any kind of matrix operations, we can do with vector processing. And vector processing, there's special vector registers. So it would be a register with, obviously instead of one 64-bit register, it would be a whole vector of registers. And then special instructions that say, here, take this vector register and do this thing to everything in that vector. And evidently ARM has vector extensions. I did not know that until this semester. But in the book, I think they talk about the x86 extensions for vectors. This one, run different programs on the same data. My head has a hard time getting wrapped around what kind of application that would be. You could argue, again, like I said last time, fault tolerance might fall into this, where you'd say, but it's running the same program. So I don't know if that falls in there. But I don't know. Does this exist? Good question. So multiple instruction, multiple data is saying, I'm going to run two different programs at the same time. So that's what this is. And we talked about threads a little bit. That's what threading is, right? Or running two processes at the same time. You have two cores, you can run two things. I don't think, well, I don't know. My iPad right now is running Zoom and looking at something in Notable at the same time, right? So it's got two things running. Or maybe you have a computer, probably you have a computer with multiple cores, so it can run two things at once and threading. And so shared memory processing, which we'll talk a little bit about, is a single address space for all processors, right? And that's so when we talked about virtual memory, that's when we said, oh, you can't have, so if each program, so if there's a single address space for all the programs, but I have different programs running, if I add up the address space I've allocated for each program, it's actually more than main memory. And so that's why we have virtual memory, right? So whatever program is running right now, maybe that whole program hasn't been loaded into main memory, right? Okay. So we're going to do just a really quick review of UMA and NUMA. So if I have cores, there's two different options for doing this. UMA is uniform memory access. So we've talked about this could be a data path, you know, like the ones we studied, this could be a data path and this could be a data path. Each one accesses shared memory and it's uniform. So everybody shares all the memory, right? So the same amount of time to process any memory location. NUMA is where I have a processor and it has its own little personal like memory dedicated to it. So this is non-uniform memory access. And so this one has its own memory and it's faster, right? So this is fast. And this is fast. And fast. But if it needs more, it can kind of borrow from others. It's going to take a long time. So that's going to be almost like not quite as bad as a page fault getting it from disk, but it's going to be there's going to be a price to be paid for using others' memory. So this is general purpose, you know, maybe your laptop probably has this, you know, any kind of general purpose computing is going to use this. This, like real-time computing, when you have to, you know, running this thing depends on being really fast, right? So maybe a car, spaceship, right? So any kind of real-time processing. I never did this, you know, in my career. I never did real-time processing, but it happened, you know, so I worked at the Applied Physics Lab, and we have what was called then the Space Department, and they programmed things for spacecraft, and they did real-time processing. It's got to be fast. You know, you're piloting, you know, remote piloting some spacecraft. It's got to be fast and it's got to be right. So I noticed, I don't know, there's something, it was in the news, you know, we launched something that's going to try to change the course of an asteroid. I don't know, I forgot what it's called. START, I think it's called, came from the Applied Physics Lab, my former place, although it's getting farther away from me, you know, as time goes on, but evidently that came out of the Applied Physics Lab. START. It's going to knock an asteroid off course. There you have it. All right. So let's do one of these because we have 10 minutes left and then we'll finish on Friday. So on Friday, I'll finish, I'll do a couple more of these Amdahl's law things, and then we'll do a little bit of virtual memory. on Friday, and then Monday, when you're not at all worried anymore about this project, we'll do a review for the final. How's that? Okay, so let's remember Amdahl's law. So do I remember it off the top of my head? So Amdahl's law. It seems like, I don't know, it seems like it's a wonderful thing, but this guy got his name on this for just algebra. I don't know. Like, okay, so the idea of Amdahl's law is the amount of speed up you get is going to be hampered by the amount you can't parallelize, right? So you really, the amount of, it's how much speed up can I get from parallelizing this code? And it's going to be limited by what you can't parallelize. So we have F is the fraction I can parallelize. And so the speed up is going to be I guess improvement. So I guess this probably, it seems like some of this is, it's getting, well, it's doesn't take long for things to be dated in computer science, but I think this was more along the lines of when vector processing and the Cray and all that were really like hot topics. The amount you can speed up this thing really is going to be dominated by what you can't parallelize, right? So if you have certain instructions that can be run sequentially, that's going to hamper how much speed up you can get. So here we have a shared memory processing system has 4 processors. The amount of a program consists of a section that must be executed sequentially and requires 10 seconds. The remainder of the program can be parallelized and requires 90 seconds. What is the speed up? So we're going to have, in this case, the speed up is going to be the fraction that can be parallelized is 0.9, and the factor of improvement is 4. So here, and I didn't even do Amdahl's law. So if I did Amdahl's law, it's going to be 1 over, and maybe on a Friday we'll do the, so this is going to be 1 over 0.1 plus 0.9 over 4. Would be the Amdahl's version, and it better be 3.08. Let's see, and then I'll let you go. Come on, calculator. My phone decided it didn't want me to use the calculator. 0.9 divided by 4 plus 0.1. Yay, yep. So this is actually a pretty good one, right? So we added 4 processors and got a speed up of 3. It's actually not too bad. But our speed up went, so the maximum possible we could ever get would be 4. If you could parallelize the whole thing, you'd have speed up of 4. And even 10 seconds or 10% serial made our speed up go down from 4 to 3. So that is the point of this. Okay. Okay. I am not going to do this next one with 5 minutes to go. So any questions for now? So we'll talk about this more on Friday, and then we'll talk about, so definitely virtualization and parallel processing are going to be on your final, but there's going to be other things on there too. So we'll talk about that next week, when you're more in the mood to talk about finals. How's that? All right. So how is the trace set up? What do you mean? There's trace files available to you if that's what you're asking. You should go look at them. How you create them, you can create them, actually the Valgrind, there's tools you can use to create trace files. But you should look at the trace files and you'll see how they're set up.